Hello, everybody. Welcome back to Couch of Science. My name is Michele. I will be your host for tonight. Today, we have a very special episode. And today, with me, there are other people that are going to help me to dig into this very, very complicated topic, which is not at all my field. And I introduce just Anna. Hello, Hannah. How are you?
Hi everyone, how are you?
All good, all good, all good. And also Renata. Hi, Renata.
Hello, everyone.
How are you?
Good, and you guys?
Good, good, good. So, for this very first part, we are going just to try to have a small introduction about what we are going to talk. But we are also going to ask you guys to stay with us, share, ask questions if you have comments, whatever you want. And we are going to have actually a very small surprise for you because it's actually a very fresh news what we are going to discuss today. Probably Anna will be much better than me to explain this. So I just leave the stage to you, Anna. So what we are going to discuss today in brief.
Well, we have three guests from the Institute of Astronomy of KU Leuven, where I work, and they are going to tell us a story of how they saw a paper, they thought it was wrong, and in about a week, they proved that it was wrong, and they have a Nature paper on it now.
Okay, so that's very interesting. Actually, something that it's a part of how actually science works, and it's very important. And at least I never had the chance to speak directly with people that were able to disprove a paper. But this is actually the core of science. But this is possible through a system that is the fundamental system of science with the scientific method, which is the peer-to-peer. And Renata actually prepared something very special regarding this, which is a very, very small introduction and a warm-up for all of you. So, Renata, let's speak about peer-to-peer review.
Oh, yes, let's do this. Thanks, Michele. So, well, if you that are watching us, if you don't work in science, but you know someone who does, you probably heard them saying that they should be writing or heard them bragging about their latest publication or things like that. And these are very common conversations for us, but it might not be very clear to everyone what this all means. So let's say that imagine that you're a scientist and you got some amazing results that you want to share with the world. So where do you start? The step one in this process is to document your work, of course. So this is normally done through what we call manuscripts. So you write down an introduction to the topic that you're studying, the methodology that you used in full detail, the results or the data that you obtained using this methodology, then some interpretations and conclusions that you can draw from your results. And this means writing up. And after you can put together a nice manuscript, you can send it off to one publishing medium of your choice. And this is normally a scientific journal that has high visibility within your topic. So once you submit your work, it's handled by someone in the publishing medium, which we call editor, who is a scientist as well. And the editor will send off your work to other scientists that know about the topic that you're studying, but that they did not participate in the study that you're presenting, of course, just to ensure that you have an independent opinion on it. So these scientists, they will do a full assessment of your work, the relevance of your study, the methodology that you used, your results, your interpretation. And this is what we call the peer review. So the reviewers, they provide a document with all of their feedback independently to the person that is handling your manuscript. And well, this normally is focused on what is wrong or what needs to be clarified or what needs to be corrected. So this can sometimes be a bit brutal. Like the example there in the slide, I could not read past this abstract. Or also something like, why does this paper even exist? This one happened to me, so true story.
Oh my God. That's tough.
So yeah, but anyway, the overall intention of that, getting the brutal part out, is to improve the initial version of what you submitted, and obviously to make it correct and scientifically sound. So this feedback is compiled by the editor and sent back to you, the main author, requesting minor or major revisions, sometimes rejecting your work, which means you need to rethink of how to present it. And there's also some mysterious situation that is called acceptance without revisions. I've never heard of anyone that ever managed to do so, but apparently it's an option. But then you have to work on the changes they requested. And after you do it, you send it back to the editor. And maybe this will be sent back to the reviewers once again. And at this stage, if everyone is happy with the changes that you've made, and if you addressed all of the concerns, then your manuscript is finally recommended for publication. If they're not happy yet, which can happen, you go back to the previous step and you have to do more changes, and this can happen a number of times. So as you can imagine, this whole process from initial submission to acceptance, it takes at least a few months. And this system is not perfect. I could rant about it for hours and hours, actually, but I will not do so. But it does make research results more reliable because it's a feedback-based system. And in peer-reviewed journals, you have the guarantee that no one made their research results available without an independent check first. So, and just to finalize, the other cool thing about it is that actually after you publish, it's like, yay, it's done. But the story might not be over yet, because you document the full workflow, including your methodology, of course. So other scientists anywhere in the world, they can try to replicate your results using your methodology, or they can try to reach the same results using different means and to test the reproducibility. And this is actually the ultimate test of how valid your results are. And actually today, our guests that will come online soon, they will discuss a bit about this post-publishing situation and reproducibility test. So that's it from my side, and I'm looking forward to hearing their story.
Thank you so much, Renata. That was a very, very good introduction. And I already saw that there are some questions regarding this topic. And guys, since we have a lot to discuss about it, just let's put all these questions at the very end of this episode. And we will have time to discuss also with people that actually was involved directly in these kind of events. So Renata, I will gently put you in the background because we are going to be very crowded here. Thank you again and see you later.
Thank you, guys. See you later.
Thank you.
And actually, I will take then the chance to introduce the three the three scientists that are here today with us to discuss about this. Anna, actually, you know them very well, so I will let you the word. I will let you the stage and see what actually we are going to have with us today.
So we have two PhD students from the Institute of Astronomy of the KU Leuven, who are Michael and Julia. You can bring them in, perhaps. Yes. And then we have together with them a postdoc, also from the institute. Tomer, welcome.
Hello, guys.
Hello.
Welcome.
How are you guys?
Doing well. Happy to be here.
Do you have your
Yeah.
beers ready?
Yes, that is a very first question. So beer on your hand, of
Cheers.
course.
Cheers.
And I hope that also the rest of the audience is having a beer with us. And so I don't know actually if you want to maybe do a very brief introduction about yourself, because I think would be very interesting to know. And then after that, we will start directly with the topic, and we are going to discuss about black holes, because that what actually we promised to our audience. So let's dig into that. But first, I don't know. Let's start with Julia, because ladies first.
Thanks. Yeah, so I'm Julia. I am working with Anna at the Institute of Astronomy and doing a PhD there. I'm originally from Germany. I've been in Belgium for like 2 years now. Yeah, I guess that's it.
And now she makes masks for you guys too.
Don't steal my
okay.
contacts for the end.
Okay, but you're printing them with a 3D printer, or just like sewing
I have
them?
a sewing machine. So
Ah,
yeah,
wow, that's cool. That's cool. Yeah. Yeah. Thank you for your help, actually. So then we have Tomer. I will just go from the top. Sorry, from the bottom to the top. Just hi, Tomer. So
hi. So my name is Tomer Shanar. I'm currently a researcher at KU Leuven, working together with Julia and Michael. I'm originally from Israel, actually, and I did my PhD in Germany in a city called Potsdam near Berlin. And I've been in Leuven for almost 2 years now. That's about it.
Okay. So also you are a very fresh Belgian citizen in a certain way.
Yeah, I could say that.
You are still trying to understand better this stuff about beers and potatoes, which is
The beer stuff I understood quite easily.
That's good. And then last but not least, Michael or Michael. I don't know actually how to pronounce your name.
Sure.
Michael
Yeah.
is fine.
Yeah, Michael. My name is
Okay.
Michael Dulmassi, and I'm a fourth-year PhD student, also working with Julia and Tomer. And yeah, so I am originally from the United States, and I came to Belgium to do my PhD. And yeah, happy to be here.
Yeah. We are very happy to have you here, actually, guys. Because let's remind this to the audience that this is actually the first time that you share, or one of the first time that you share, what actually you did in public, because you have like a kind of embargo before, because we were talking about disproving something, so it was kind of a big deal, right?
Mm-hmm. Yep.
Okay.
Yeah,
so
no,
go on. Sorry.
No, I was just going to say that because the paper that we published was with Nature, it was under embargo, so we weren't allowed to really talk too much about it until it was released. So.
Okay. And it was released yesterday, right, or today?
It was officially released yesterday.
Okay. Wow, that's cool. So I think that we can start to go directly to the scientific discussion behind all of this. So I will just put on the screen your work. Okay, so now you should be able to change the slides without my help. And so Michael is going to introduce the research. And then we are going to take a bit of time to have a small Q&A session with him regarding this, with him and the other, with Julia and Tomer. And then after, we are going to discuss regarding peer-to-peer review and disproving and all the, let's say, human side of science, because we love also to do that. So I will shut up, Michael, and the stage is yours.
Sure. Thank you very much. I'd first like to start by thanking the organizers for inviting us, and I'd also like to thank all of the viewers for joining us today for this presentation. So today I'm going to talk to you about kind of a unexpected black hole adventure that our research group had recently, the end of last year, and it really kind of started with these headlines that we saw at the beginning of the day on the 28th of November, which is when the original Nature paper was published that claimed that there was an impossibly large black hole in our galaxy. But before going into exactly why this was such an intriguing discovery, I first want to talk to you a little bit about what black holes are. So kind of the basic definition of a black hole is it's an object whose gravity is so strong that neither particles nor light can escape. And they come in two kind of flavors, we can say. We have stellar black holes, which we think originate from stars. And we have supermassive black holes, which we're not really exactly sure of their origin. So stellar black holes are usually found with masses of less than 50 solar masses, and us astronomers like to relate everything back to the sun. So 50 solar masses just means that it's 50 times as massive as the sun. Supermassive black holes, on the other hand, they range from about a million up to billions of solar masses. So very, very different in size. So where do these black holes come from? All stars can start their life in what we call a star-forming region. If you have a star similar to our sun, what will happen is as it evolves and goes through its life, it'll eventually collapse into what we call a white dwarf. Now, if you have a star that's more massive, as it evolves, it will form other interesting objects such as neutron stars and black holes or other exotic things. Now, what a star turns into at the end of its life depends on a lot of things, but one of the biggest factors is its mass. And we don't expect to see black holes forming with masses greater than 50 solar masses. Once you get above this mass range, what happens instead is that we think that the star will explode completely and convert most of its energy into light, and then we don't actually see anything left behind. So how do these black holes actually form? Every star is in a constant tug of war. So I mean, it's being pulled down by gravity and it's being pushed up by pressure. Anything that has mass has a gravitational pull associated with it, and stars are so massive that the gravitational pull is very large. Now, inside of a star, there's pressure which is counteracting this gravity, and there's two components of this pressure. You have gas pressure, which is very similar to the air pressure that you feel around you, and you also have radiation, which is coming from the fuel inside of the star as it's being burned. Both of these two components together comprise the pressure, which allows the star to counteract the gravity and stay stable. Now, as the star evolves, what happens is that it uses up this fuel, and that fuel is no longer available for burning. So without the pressure that we're getting from the burning of the fuel, what happens is that there's an imbalance in the star. The gravity is now much stronger than the pressure, and because of this, the star begins to collapse. Depending on the mass of the star, this collapse can eventually lead to the formation of a black hole. So I mentioned black holes don't give off any light, and not even particles can escape. So how do we actually study them? There's a couple of different ways that we can study them, but one thing, two ways that I want to talk to you about today. One is we can look at the material around a black hole. And if you recognize this image, this was the first image of a black hole ever taken just this past year. And what we're actually seeing here is we're seeing material around a black hole. And by studying this material, we can understand the characteristics of the black hole in the center. Now, alternatively, we can also look at how stars behave around a black hole. So if we were to point our telescope to the center of the galaxy, what we would see is a whole bunch of stars moving around some unseen object. And this unseen object is a supermassive black hole in the center of our galaxy. So by studying the material around a black hole and how stars interact with these black holes, we can gain a lot more information about the black hole itself. Both of these concepts are very important because these two concepts are how the authors of the original paper came to their conclusions. So speaking of which, the system that we're talking about here is called LB1. This was originally published in Nature by Liu and his team. And what they found is they found a black hole that was impossibly large. More specifically, they found a double star system consisting of an 80-day orbit with a 70 solar mass black hole and an 8 solar mass star. So just like the planets orbit around the sun, in this case, we have a star and a black hole, and they're orbiting around each other. Now, one of the things that made this discovery so interesting was this black hole was much more massive than we expected it to be. As I mentioned, we expect stellar mass black holes to be no larger than 50 solar masses. And the fact that we find one that's at 70 solar masses is a real problem for the way we understand massive star evolution. This would be as if you're walking down the street and you happen to see a 200-year-old person. It may not seem like it's that much older than the average person, but in reality, this is what the situation is most similar to. So before getting into exactly how the authors came to this conclusion, I have here plotted, or not plotted, I have here an image, an artist's impression of what the authors thought the system was. So what they thought is that you have your visible star here, and you have your invisible black hole, but you have material around the black hole, which the authors study. So before going into exactly how they came to their conclusions, there's two additional concepts that we need. The first one is spectra. So if you were to take a prism and hold it up to the sun and look at the ground, what you'd see is that the sun's light will be broken up into a rainbow. However, if your eyes are good enough and your prism is good enough, what you'd actually see is that this isn't a constant rainbow. There's breaks. Now, us astronomers are a little bit boring, and this rainbow is a little difficult for us to analyze. So what we do is we convert this rainbow into what we call a spectrum. So we take the intensity that we see and plot it against the wavelength, which is just the color that we're seeing, and we come up with a plot something like this. Now, each one of these features that we see here corresponds to an individual chemical element. And by studying the lines that are present in the spectrum, we can have an idea about the chemical composition of the star, as well as other things such as the temperature of the star, the mass of the star, etc. Now, there are two kinds of spectral lines that are going to be important today. One of them is called absorption lines, and these are what you're seeing here. So these are our lines that are going down. And these are from chemical elements that are on the surface of the star that are absorbing light coming from below them, coming from the interior of the star. And as they absorb the light, we don't see as much of the light coming out, which is how you get these dark bands. Now, if there is, for example, material around your star that is giving off its own light, instead of seeing a dark patch, instead you would see a bright spot. And when we plot it, just as we plot this absorption line, instead we would see something that we call an emission line. So instead of going down, the emission lines just go up. Now, from our knowledge of atomic physics, we know exactly where all of these spectral lines should be. However, every once in a while, we'll see that the entire spectrum of a star is shifted. This shift tells us about the velocity of the star. So I want you to picture yourself standing on the side of the road, and you hear an ambulance approaching. As the ambulance is coming towards you, it is a much higher pitch, a much higher frequency. However, when it passes you, it then has a much lower frequency and a much lower pitch. Light behaves in the exact same way. So when you have a star that's moving very fast, here we're focusing on the yellow star. If you have a star that's moving very fast and you were to look at its spectra, you would actually see that its spectrum is shifting based on the orbital motion of the star. When the star is coming towards you, its light is at a higher frequency, so shifted towards the blue. And when it's moving away from you, the light is at a lower frequency, so shifted towards the red. Now, if we were to take spectra of this system all throughout the orbit, what we would be able to construct is something that we call a radial velocity curve, which looks something like this. We can plot the velocity of the system, so pretty much this shift, as a function of time, and we can actually see how this system moves. Now, if instead, right here what I'm showing is just the yellow star giving off light, but if the blue star is bright enough, then it can give off light of its own. And what we would see is that its spectrum is shifting in the opposite way of the yellow one. So when the yellow star is coming towards us, the blue star is moving away from us and vice versa. And this is reflected in the spectral lines that we would see. Now, by looking at how much each star shifts, how much the spectral lines of each star shifts, this gives us information about the masses of the stars. To kind of explain this a little bit better, I'm going to take us to the Titanic, and I want you to recall the scene in the Titanic where Jack and Rose hold hands with each other and then start spinning. Jack and Rose are around the same mass, so their speeds are around the same, or very similar to each other. Now, if Jack were to instead decide to spin around with his cat, what you would find is that his cat is moving much faster than he is, and it's going to look much more similar to the situation that we have over here, where Jack is the yellow star and his poor cat is the blue star. So by measuring these shifts, the shifts that we're seeing in the spectra, and computing our radial velocity curve, we can determine the relative masses of the two objects in our system. So now that you all are experts on radial velocity curves, I can actually show you some of the real data that the authors originally used. So what they saw in the spectra of this system is they saw most of the lines shifting in the same way. And these lines were associated to the visible star. So when they plotted all of them, and they fit a curve to it, which is this purple one, they came to this radial velocity curve. However, the authors noticed that there was one particular emission line that didn't behave like the rest of the lines. This emission line, when they measured the radial velocity of it, appeared to go in the exact opposite direction. Now, this is exactly what you would expect if you're seeing a binary system. So what they looked at is they looked at an emission line. However, I've cut off the top of this emission line because there's a lot of complicated things that are happening at the top, and they're not so important for this. What the authors saw is that when they looked at the emission line, they saw that it was just moving ever so slightly. And that's how they got this orange curve. Now, I want you to recall the Jack and Rose analogy that I mentioned before. Based on the ratio of this visible stars curve to the emission line curve, they're able to determine the masses, or the mass ratio of the components in the system. So by looking at the spectra of the visible star, they're able to determine the mass of the visible star to be around 8 solar masses. And based on the ratio, they're able to determine that the black hole, or the unseen companion, should have 70 solar masses. Now, this was, as I mentioned, a very big finding because we shouldn't see black holes that are 70 solar masses. And this really hit the astronomical community a bit hard. How do we explain something like this? So the theorists decided to go look at their theory and try to come up with ways that they could produce 70 solar mass black holes. And the observers looked at the data and looked at the results that the original authors had published and tried to figure out a way that maybe there was something that they missed, or maybe they didn't analyze the results properly. We here at KU Leuven are very lucky that we have access to the Mercator telescope in La Palma. So we quickly called up the observer who was observing at the time and said, "Will you please take a spectrum of the system for us?" And the observer very nicely took a spectra for us and allowed us to analyze this system ourselves. So the first thing that we want to do is we wanted to look at the spectrum and see if we could measure the shifts in the spectra and determine the radial velocity in the same way that the authors did. We know what time the spectrum was taken, so we know what the radial velocity shifts should be at that time. And when we plotted them on top of what the original authors said it should be, what we found is that it matched up perfectly. So we thought to ourselves, okay, so we can reproduce their findings. We are able to show that we can reproduce the radial velocities that the original authors found. However, we thought to ourselves, okay, is there some other way that you can make this exact same curve or reproduce these observations without needing a 70 solar mass black hole? So we thought about it a little bit, and one thought that kind of stuck with us is that, right where this emission line is, that the authors are using to measure the mass of the black hole, right where this emission line is, there also happens to be an absorption line that's associated with the visible star. So we know that this absorption line should be moving back and forth. What if instead of this emission line that the authors saw that was moving, instead of that emission line moving, what if instead it's just a stationary emission line and a moving absorption line? What if the motion that they were seeing in the emission line was only an effect based on the motion of the visible star? So if we were to add these two curves up and add a little bit of noise to make it look more realistic, we get something that looks like this. A little hard to tell, but if we zoom in on the very edges of the plot, we can see something that looks like this. So what we're able to show here is that with just a stationary emission line and the moving absorption line of the star, the visible star that we see, we can reproduce these results very accurately. So what this means is that instead of this emission being due to material around the black hole, which is what the authors originally interpreted this as, instead, if you have emission that's around the system as a whole, or some emission that's coming from a cloud either in front of or behind the system, you would reproduce the exact same things. This was very exciting for us because this means that we can reproduce the observations without needing a 70 solar mass black hole. And while I'd love to take all the credit for this, this was very much a group effort. We were able to prove that you don't need a 70 solar mass black hole to do this. And our research group, unfortunately, 3 of us can be here today, but our research group is very large, and all of us have participated in this. And I will also mention that at the same time that we came to this realization, there are 2 other independent groups who came to the same realization. One using the exact same technique that we did, led by El Badri, and another investigation led by J.J. Eldridge and his team, who took a more theoretical approach to this. So our stellar evolution theories are still valid. This is indeed a very interesting system, and I'm sure it'll be the subject of many studies to come. So thank you very much.
Thank you so much, Michael. It was oh my God, it was a lot, but was very interesting. And thank you for your explanation. Was really clear. At least for me, having a little of background about spectrum and all this stuff. But I think that we have actually here today in the audience people that is very ready to have ask questions. To put all of you in danger, I would say. So I will just open the Q&A session. I will say that is going to go on for 10 minutes probably. And so if you have questions, just shoot it. Anna, I don't know if you have questions actually, or if you selected already something. Otherwise, I can actually ask a very stupid question.
No, go for it.
So my very stupid question
is... There is no such a thing as a stupid questions, Mikel.
So my very stupid question is, so you were mentioning that actually you were able to have data directly from a telescope, but how actually is this possible? I mean, this black hole, actually, this is not a black hole as we said, but this system is very far from us. So how is possible that this telescope is able to gather this information?
Do you want me to take that, you guys, or Yulia or Tomer? Do you guys want to? Okay, I can. Sure. So, sure. The telescopes, the way they work is they have a very big mirror that collects a whole bunch of light that allows us to pretty much focus all of the light so that we can see very, very faint objects in the sky. So by just by the fact that their mirrors are so large that they can collect so much light, it kind of amplifies the light that we're getting from them and allows us to study these very faint and very distant objects.
Okay, so it's basically a huge piece of glass, I would say, in a very simplistic way.
Sure.
Okay.
I've seen a question in YouTube, I think. So if you guys, people in the backstage, can pin it in the screen so that everyone sees it. But it's a very interesting question. So you just said that that you don't need a 70 solar mass black hole to reproduce this data. So what is it then? There you go. So I think this one is for Tomer, because I know that he has recently been working on trying to understand what it is. So if you want to give a bit of an explanation of what the system actually is, or what you think it is.
Yeah. So I'm really involving now everyone in the happenings of the last days. So first of all, you should know that up until a few days ago, people had really no idea what it is. It could be a black hole of a lesser mass. It could be a neutron star, what Michael already suggested, the white dwarf. People suggested also it's a faint normal star. So there were a lot of ideas, but we were not lazing around. We were really collecting a lot of data, trying to understand what is hidden there. And we have just published, we have just submitted a paper in which we claim that the supposed black hole is in fact a very rapidly rotating star that was missed in observation. But this paper has not yet been refereed. It has not been reviewed, and it's not officially accepted. And you all know what it means because of Renato's introduction. So we still need to have it confirmed. But this is our current idea. It's a very rapidly rotating star.
Oh, wow. And is the first time that actually something like that is observed? A star so fast?
They're very, very, very rare, very rarely observed. And when they're observed, usually they're not observed with a companion star next to them. So the system that we observe now, if we understand what we're seeing, is indeed extremely rare, even if it is not a 70 solar mass black hole. This rapidly rotating star together with the other star, without boring people in the details, I can just say that it's a very rare system, and very interesting for astronomers, at least.
Okay, that's very interesting. Actually, it's actually we have a question from Dominique. I have a question. Out of Jack and Rose, who is the visible star?
Sure, so I can take that one. I'm going to actually refer to this to, instead of Jack and Rose, I'm going to talk about Jack and his cat. And in this case, his cat is the visible one, and Jack is what the authors originally thought was the black hole.
Okay. Which actually is more or less, correct me if I'm probably wrong, this is the same way actually they were able to take the shoot that you show about the black hole, right? They were able to use the light generated from stars that were around that black hole to have that shoot, right? Something like that.
So I think that the image of the black hole was just from the material around the black hole kind of glowing. I don't think it was in the starlight around it. So.
Okay. So it was even okay.
Yeah.
Very interesting. So
sorry.
No, go on, Anna. If you
I
have
got two more questions, but these ones were asked in the video party that I started, so I don't think they appear in the Pint of Science wall, but I can just read them for you. So Dennis asks, why is radiation so important for the lifetime of a black hole? I don't know if anyone wants to take that one. And then the second one is by Glenn, who says or asks, what is the origin of the stationary H alpha line then, if it's not moving? So I don't know.
Very tough one.
I can talk about the second one. I think none of us is really a black hole expert here. We're more working on the stellar side. So as Tomer just explained, we don't really think anymore, given that we now have way more data, that there is really a stationary H alpha line. But if there was one, then we thought it would be around the whole system. So not just you have a star and a black hole and the disk around the black hole, you could have a star and a black hole and a disk around the two. So we know at least one system where you have two stars and the disk around the two. And I think Glenn actually is working on these as well. But so that was the idea. And then the emission line that we see that is tracing this disk does not follow the motion of the black hole. So then the conclusion that was reached by the Nature paper doesn't hold anymore, because that was the main thing they implied, is that the emission line is following the black hole. But if it's not, then all the mass estimate and everything else that follows is not plausible.
Wow.
yeah.
Okay. So I don't know if we have other questions. I think that there is one here from Maggie, which is asking, so is it a binary? But I think,
Yeah, so I mean, now what we think is that it is indeed a binary, as Tomer was saying, that we have the visible star, and then we have the rapidly rotating star as well. So it's two of them. At least that's the current interpretation. But anyway, we do see the shifts in the radial velocity, which also indicates that it is indeed a binary. So.
okay, perfect. Very clear. Very clear. So while I leave a bit of extra time to the audience in case they have other questions, I just want to advertise for the next event that we are going to have here in Couch of Science. The 7th of May, we are going to discuss about earthquake with a special. We are going to discuss not just about earthquake, but also the impact of human being on geology, actually on the world, on actually how the world rotates and similar. So in a very interesting topic. Probably I'm saying something not very precise, but Renata, probably she's the best to advertise this. But for now, we don't want to share with you so much information because we want to do a surprise as was for this one. And then the other thing that actually, if you're still hungry for science after us at 8 p.m. Belgium time, there is another event for Pint of Science UK. Where actually they are again talking about space and astronauts with the Space Talking with an Astronaut. And you can have all the information in the website that I hope, yes, the guys in the background, they just promptly upload here the event, and you have all the information there. So if you want to also have a look of that, just go there and say that Pint of Science Belgium send you. And so I think that we have one question from Wundt, I guess.
Yes, the last one.
So this one, I guess.
Yes.
In the case of a rapidly rotating star, how close will this rotation be to the limit where the centripetal force overcomes gravity and at the equator? Oh my God.
Question that only one person can appreciate. Who is it aimed for? This question.
Go ahead, Tomer.
Yeah, go ahead.
Yeah.
So we actually call this star a critically rotating star, and critically rotating means exactly that. What is written in the question, that it rotates as fast as it can. If it would rotate any faster, it would start spewing material across its equator. So it's rotating as fast as it can, and the idea is that it has accreted mass in the past. But like I said, it's still our theory. It's published, it's online, so you can go and read it, but it wasn't yet reviewed, so I should not.
Yeah, but so you're saying that in theory, a star can rotate so fast that actually fell apart. I mean, there is a limit of
there
the rotation.
Limit, yes.
There is a limit actually after which actually fell apart.
Each star has a limit of how rapidly it can rotate. The sun rotates quite slowly. It could rotate a lot faster. Yeah.
Okay. Because we always talk about, how stars collapse, but actually it's not very popular, I would say, how stars actually fell apart, So if they can explode in a huge supernova, I guess that is probably it's the name for a star that explodes, something like that. I don't know, guys. For me, all of this is super fascinating, but I have really huge science holes regarding this topic.
Okay, so yes, supernova is an explosion of a dying star, but not because of rotation.
Yeah, no, of course. It's actually
if a star rotates critically, as we say, very close to the limit that is mentioned in the question, then it cannot support the material. The gravity cannot keep it together anymore in the star. This is in fact why they can build disks around them, because the material starts gathering around the star.
Okay. That's very interesting. Thank you so much. So I would say that actually we can go on with the following topic. So let's talk about something more relaxing, probably not maybe for the three of you that you face this challenge, but actually you overcome them and you were quite successful. Before actually we mentioned the paper where actually you published, which is Nature. And if some of the guys in audience they don't know, is one of the most, or maybe the most important science journal that we have currently. And so this is a really good achievement. But actually, what I would like to ask you guys, if you can share how all this started. So this paper was published, and then someone just came out in your team saying, guys, this is so wrong, so we have to do something about it. So how does it work, actually? How everything happened in the beginning?
I think they're questions for me because I'm typically the one who's always awake first. So, actually, on that day, I was in the office and I saw it online and I sent it to the group. And I just checked before to be sure, but like before lunch, we already had like 10 or 15 emails by people from a collaboration that we're in that work on massive stars, talking about it, discussing this is weird. Why do they find such a massive black hole? What could be wrong in their analysis? So people were already looking at that. And by chance, we had our group meeting that afternoon. So in that group meeting, we already discussed what exactly they did. We looked at their methods. We looked at what they've done. We looked at the data they've used. But of course, the thing is with the data, we cannot see the data itself. So the only thing we can see is the plots or the figures they produce. So our first idea was, as Michael said before, we need our own data. So we need a spectrum of our own that we can actually analyze. And yeah, that was the first thing we did, is to check whether our telescope, the one that Michael mentioned, the Mercator telescope in the Canary Islands, whether we can actually observe that star quickly, if it's bright enough, if it's visible at that time, and also if the observer is willing to do us a favor. So yeah, that was the first things we've done. And then we got a spectrum so we could start analyzing.
Okay, so basically in the paper, there was the plots, all the spectrums that actually similar what Michael shared with us. There was probably, I guess, also the position of the star in the galaxy, like the coordinates or similar. But there weren't actually the raw data. So what actually is the basic data where they used to analyze then. Okay. Is this something weird, or it's the case for? It's not the case. So
that is typically the standard.
Okay.
Whenever you get data, it's like your own for like a year.
Okay.
When you publish something, you mostly publish your results, but not the raw data. So that is quite standard.
Mm-hmm. So it's not that common actually to share raw data with with the science community.
If you're asked, I would say yes. So once we had our data, we were asked for it. We shared it, actually with the original authors.
Yeah.
So it depends.
But in the end, this paper was from a Chinese group, right? If I'm not wrong. So is it difficult to obtain raw data or data from other countries or other continents, or like in a situation like China? Or they have like some rules that they don't have to share, or they don't want to share? You don't know. Really.
That in general depends. Also, the data they've used were partly from their own telescope in China, but also from a telescope in Hawaii, and also from a telescope next to the one that we're actually using in the Canary Islands. So it's a mixture of data, and it's also a big collaboration, right? It was people from all over the world.
Okay. So basically, you noticed that there was something wrong, and you just decide to close yourself for 2 days in a room, right? No, this is very interesting. I mean, could you share actually some episodes that how you worked there? Because you were like, as you share, Michael, you share a picture. You were, I don't know, 15, 16 people in that picture. So how actually was it? And this is a question for all three of you. So it was crazy. You almost kill each other. It was very nice. How was it actually? You fight a lot, or you just discuss very friendly? So how was it? Because actually this is something very interesting in the science stuff, because it's the human point of view. So the scientists actually are human beings that are doing something, and probably this is very interesting as well. So how was it to stay there for 2 days, and why you did that actually?
So I mean, yeah. So as Julia mentioned, the paper came out on a Thursday, and we saw the paper, and then we asked the observer to, we discussed it a little bit, and then over the weekend we decided that we wanted to ask the observer for some Hermes data of our own from the Mercator telescope. We emailed them on Monday and asked them, and then on Tuesday night they took the observations. On Wednesday we had the observations, and then on Thursday we said, okay, we need to analyze them. So then it was Thursday and Friday were the 2 days where we were holed up in one of the conference rooms that we have in the institute. And Thursday we were analyzing the data and trying to figure out what we could find. And Thursday was also the day when we ran the simulations, and they first came out positive, showing exactly what the authors showed. And then so we said, okay, we need to write this up, and we wrote the paper up starting on Thursday into Friday, and then we submitted it on Friday evening. So it was a very, very quick process.
Wow. Okay, so you submitted already by the end of that week. I thought that actually you are just a brainstorm. Oh my God, this is impressive, guys.
Yeah. So
this is impressive.
Yeah, a week and a half after the paper was the original Nature paper was published, we had submitted our paper.
Okay, and this is actually to actually have a timeline. So this happened when last year, this year?
Yeah, this was November of 2019.
Okay,
the end of November of 2019 into December.
Okay, and then actually there was all the period of peer-to-peer process, which actually was until now, or was a bit before then now?
Yeah, till basically now. I mean, we had we had the referee report that we had to address, and then also just the publishing in general takes time for that to happen. So the paper was officially published and released yesterday on the Nature website.
Okay, but so actually this is impressive, because to take so much. I'm quite shocked. I would say, guys, because I also had to write articles, and it's terrible. And usually the ability to be so quick, it's very unique. So that's crazy. And again, I don't know how it's possible that all of you came out alive from that room, because it's quite impressive. Anyway, guys, from the audience, if you have any questions for these three amazing scientists regarding this topic, so peer-to-peer review, how to publish, how can be stressful to write something, if you need actually tips regarding the work that you are done for writing something, this is a good moment to ask. We are going to be here for a little while more, and then actually you have the chance to share with us. But after this, basically you came out, you have this paper, you just submit that, and then actually you went to celebrate, I hope.
So it's actually funny. We had there was a reception happening in our institute on that Friday. So we were there hanging out with the other people in our department, and a few of us are running back and forth to the computer to make a quick plot to send to our advisor, who was compiling the paper and everything. So on Friday, when the paper was finally submitted, it was really a big relief for all of us, because it was quite a hectic couple of days, but it was really fun. It was a really cool experience to have all of us in the room, all of us working on the same thing at the same time, and really pushing everything through. So it was really cool.
Okay. And how many nationalities, actually, if I can ask, were there? I mean, 15 people. Just all the three of you, it's just 3 different nationalities. So I cannot imagine how many nationalities there were in that room, actually, at that point.
Check the slide with all the pictures and count.
Yeah, I think there's either 2 people with the same nationality in our group.
So let's have a look, actually.
Maybe 2.
Very quickly, because no, because this is very interesting, and also it's crazy because it makes you can understand actually how powerful can be science to gather people all around the world to the same scope, which actually is not to kill anybody, it was just to find an answer to a question which is very...
Well, they kill a black hole.
Yeah. yeah. Okay, that's true. But so you are here, I see, so 15, 17 people?
Yep.
And so probably
maybe 10 different nationalities in there.
Oh my
if I
God.
had to-
That's awesome. Wow. Very cool, guys. Very cool. So do we have a picture of a black... Yeah, so actually, coming back to the black holes, Maggie has a question that... so do we have a picture of a black hole? It's... Actually, yes. Michael is going back to the picture, and I think, here we go. Maggie, this is the picture.
Yeah, so the left picture here is actually the only picture that we have of a black hole. And this was taken just last year through a collaboration of a whole bunch of telescopes all across the world coming together to make this picture. So yes, we have exactly one.
Okay. Very good. And so, guys, I think that we are going to the end of this our discussion. And since we are still in this weird moment with this quarantine and stuff like that, also the last picture that you shared actually was a picture taken, I think, with Zoom probably during one of the. What was that moment? You were celebrating for the publishing, or you were just discussing? What was it?
That was earlier today. I told everybody in our group meeting that we had today to smile because I wanted to show their pictures today.
Okay. Makes sense. That's very cool. So, but coming back to that, it's something that we are doing since the beginning of this format. We are asking people that actually are with us during Couch of Science to share with us a way to fight the quarantine. You know, boring way. Actually, Julia has a very nice way to fight it, preparing masks and stuff like that. But maybe she has something else. So in the past, we have crazy ideas like, I don't know, staring at the people outside of the window for who knows why, TV shows, video games. So do you have something to suggest to our audience? Maybe, I don't know, a good documentary or a good interview, or maybe just, I don't know, a paper or a book, your favorite book, I don't know, something like that. But it's just to share this with the rest of the audience. Who's going first?
Yeah, I can go first. I've been reading more now that we're in quarantine. I've had time to read more, so I've been enjoying that, and I've been playing more video games. So yeah, that's what I'm doing to pass the time.
Okay, can you suggest us a book or a video game, or both, if you want?
I'm currently reading a book called Elantris by Brandon Sanderson, and I'm enjoying it. So yeah, I would recommend that one.
Good. And Tomer and Julia, do you have something to recommend to fight this the boringness of the quarantine?
I can say something. My colleagues will laugh because they know already that I'm crazy for plants. You can use the time to plant something, to take care. You don't even need, I was going to say, to take care of your garden. I have a garden, so I'm lucky. But you can just put something on a balcony or in a pot, and when it comes out of the ground, you'll be happy to see it.
Yeah, makes sense, actually.
Nice thing to
do. Unfortunately, I don't have a garden, so I cannot do that. And all the time that I try to buy a plant, you know, like basil or rosemary, they just died after 10 days, 5 days, not even 10 days, 5 days. Probably because I'm not able to take care of them. Probably. Tomer, for you, what actually is a good way to fight this quarantine?
So I don't think it would apply to almost anyone, but I've been spending a lot of time doing science. The quarantine kind of down and write and work on projects that you left open. But I also started watching a series that I watched a long time ago called Twin Peaks.
Yeah. Actually, you are in the good moment because it's like 30 years anniversary. I think this year is the 30th year anniversary.
I never watched the third season, so I thought like I should watch it again with my partner.
Yeah.
Here's my to everyone.
Okay, perfect. So, oh my God, it was a wall of text of question probably. I don't know. Anna, can you have a look while? So,
Yes.
guys, what actually I want just to share with all of you. So, again, since we are going to the end of this episode, if you have questions, if you want to share with us something, if you actually have ideas for this show, if you know someone that would be interesting to participate or similar, just let us know. Here you have all our contacts. So you can follow us on Facebook, on Twitter, on Instagram, and also on YouTube. We have a channel that actually is alive now thanks to this Couch of Science event. Or you can just directly send an email to us, and we are going to reply to you promptly. And guys, thank you so much, Michael, Julia, Tomer. Thank you to be with us. It was a real pleasure. And again, congratulations for your achievement. Was impressive. Was really impressive, the work that you did, and brings our congratulations also to the rest of the team, because it was a great, good job. And thank you to Renata. That actually I will put her back for a moment for the brief introduction, but very interesting about peer-to-peer review. And thank you to Michael, which is in the background and is helping us. I will try to bring him inside for a very small moment. Here we go. Hello, Michael. Thank you so much for your help on the background, because without you and without Renata today, probably we were going to sink in all the technicalities. And that's it, guys. For today, I think we do... What?
We tried to understand the question, but it was a pain.
Yes, I actually want to tell Michael, Julia, and Tomer that maybe you can pass by the Facebook chat of the video later, because there are some questions that, because they were maybe too specific, we didn't pass them in to because this is Pint of Science, it's supposed to be accessible to everyone and so on. So please go to the chat and have scientific discussions with these people that we left behind.
And actually, it would be also nice if you could share with us the links of your article, or at least something to read regarding that. So if someone wants to dig in it, he can do it without any effort. And so, guys, thank you so much. For the audience, thank you to have been with us. And you can follow us up, because next week we are coming back with another event. We are going to discuss about geology and earthquake, and in the future we are coming with more events. So probably we are going to stay with you until the end of May, at least. And actually, if you like it, we can go even further. But let's see actually how it's going. And Anna, Michael, do you have something else to add?
No, that's it from me. Thank you, everyone, for tuning in.
Was perfect.
Thank you so much. Thank you so much.
Yeah, thank you for having us.
Bye, guys. Have a nice evening. Bye.
Enjoy the long weekend.
Bye.